Hello and welcome to this evening's webinar event on VCE Mathematics, Probability and Statistics with Pizzazz. This is one of the series that we are hosting for the new VCE, well, the revised study design. If you take a look on the Texas Instruments Australia webpage, you will see a series of about 10 or so events that we have in support of the revised study design. Now, I'm delighted to be able to introduce one of our best presenters this evening, panelist Mr. Frank Moyer. Good evening, Frank.
Good evening.
You can see on the screen there that Frank has extensive experience in teaching VCE mathematics in all subjects and also one of our T-Cubed Australia main national instructors. I'm just going to hand over straight across to Frank. I will be in the background. If you have any questions, please type them into the chat and I will try to either answer them myself or refer it over to Frank. Okay, we can see your screen clearly, Frank.
All right, excellent. Well, thank you for that introduction, Brian, and good evening and welcome everyone. Okay, so tonight's webinar, Probability and Statistics with Pizzazz. So what we'll be doing is looking at some of the ways in which dynamic features of TI-Nspire can be used to create interactive manipulatives and to assist in the teaching and learning of some topics in probability. So what we'll be covering is looking first of all at the binomial distribution, the distribution of continuous random variables, including the normal and standard normal, and then some sampling distributions. Now, I'll only be sampling a bit of each of these 5 activities that I've created. So there are 2 brand new activities, so new in fact that they're not on the TI Australia website as yet, but they will be by this time next week, and I'm sure that you'll be emailed a link to these activities. So there's one on binomial graphs, another one on graphs of continuous distributions, which will go up on the website very soon, and I'll also be referring to 3 which have been there for a few years on the distribution of sample proportions and confidence intervals. All right, so first of all, I'm just going to show you some of the manipulatives that I've used in this activity called binomial distribution graphs, and you'll be able to download the student activity sheet, the teacher notes, and the TI-Nspire file. And I'll just be looking at some of the manipulatives. All right, so with the binomial distribution, there are several ways we can represent the probability mass function. That, incidentally, is what the study design calls it. We can have an equation, we can have a table, and we can, of course, have a graph. And the graph is what we're going to concentrate on. So we're going to have a look at the binomial distribution where we've got 10 trials and differing values of P. All right, so a good place to start with Nspire is with a spreadsheet. Now, I've got a notes page here, and in this notes page, I've written down some of the formulas that I'm going to use in the spreadsheet. So there's first of all the sequence command. I want a sequence from 0 to 10 because I've got 10 trials. Now, the reason that I'm doing the sequence command rather than just filling down 10 spaces is I could then change the 10 to an N and have a slider controlling the N. So I'm going to go to the spreadsheet, and under the column which I've labelled X, I'm going to I'll copy that formula and I'm going to paste it. And I get my numbers. And I can do the same with the probability function. So I'll copy that, put that in whoops, that's fine. So I've got a table of the probabilities. In the third column, I'm going to have the product of the two, and if I sum that product, that gives me the expected value. Now, wouldn't it be good if I could see the slider and the spreadsheet side by side? And one way that you can do that is you can go to Doc and Page Layouts and Group, and it will group the two adjoining pages. And you can then control how you want to divide that up. Now, with the software, you can just grab it with a mouse and move it across. With the handheld, it's rather similar, but you just use the arrow keys. All right, and once I've got that the data in the spreadsheet, I can then create the graph. Now, in order to save time, I'll go to one that I've already created and talk a bit about the architecture of the page. So I'll start with the graphs application. I always prefer to do it this way in the first instance with the binomial distribution to really emphasize that it's a discrete distribution. So I've done this in just a normal graphs page, and I've put a slider in there, and as I change the value of P, I can see the shape of the distribution changing. All right, so when P is a small value, I can see that I have a positively skewed distribution, and this value here is the mean, and I know it's, or the expected value. And how do I know that? Because what I've done is I've got the sum of the x times the probability, which I had in the third column, in the one that I prepared earlier. All right, so how did I get these dots here? Well, I had the spreadsheet, and then if you, in the graphs page, if you then go Menu and Graph Entry Edit, you'll see that one of the options is Scatter Plot. And under Scatter Plot, you can just select X for along the horizontal axis, and the column that I called prob for the probability for the vertical axis. And then I just rescaled the axes so that I zoomed into the data and just added a slider. Adding the slider's easy. It's Menu, Actions, and if you go down to B, you can insert slider, and then just edit the slide, and then change the settings for the slider. Now, these dotted lines here, rather than just having dots there, all I've done there is just a segment. So a segment is just Menu, Geometry, Points and Lines, and one of the options is Segment. Okay, now this line here is X equals the sum of the column which I called XP, which is the product of X and its probability. So how do I enter that? Well, once again, it's in the graphs application, Menu, Graph Entry Edit. This time I want relation, and one of the relations that I've got is the sum of XP. The other one is 10 times P. And if you hover over, you'll be able to get this manipulative yourself. It'll be downloadable from the website within a few days. If you then hover to it and you press the tab key, it will cycle through everything that's in the vicinity. And one of the things you can see is that the expected value worked out from first principles is equal to 10p, which is reassuring. Okay, so that illustrates the effect that P has on the distribution when the number of trials is constant. And there's a series of questions associated with this. It isn't just the manipulative, there actually are activities for the student to do. Okay, so the other one, what about the effect of changing the parameter n, the number of trials, as well as the probability of success in a single trial? This time, just for something different, I've done the same thing, essentially the same thing, but I've used a data and statistics page. So I've got my spreadsheet as before, except this time I've changed the sequence command to, instead of being from 0 to 10, it's from 0 to n, and the slider controls n. And likewise, the probability, I've replaced the 10 with the n, and the slider's controlling that as well. All right. So this time, I've got the similar sort of setup, except it's in the data and statistics page. So that's the effect of changing P as before, but I can also see the effect of changing N. And this time, and you can see how the expected value or the mean value changes. Now, how did I enter that in this application? Well, once you're in data and statistics, one of the options you have is under Analyze, is to add a plot value. So you can change the name of that plot, which I called expected, and then put in your formula, which in this case was the sum of xp. If I wanted to, I could have another variable called n times p. And we see that, in fact, it's exactly the same value as expected value, and the other variable that I called n times p are in fact coinciding. They're exactly the same thing, irrespective of the value of n and p. So that convinces students that the expected value really is np if they can't sort of see it intuitively. All right. So this is the same thing, this time in the graphs application. So either application works, but in the first instance, I always like to show discrete points rather than the histogram. I use the histogram later, especially with the sampling distribution, as we'll see towards the end of the webinar, where we're actually using the normal approximation. Okay. So once again, you can do the same thing using data and statistics application in and get the histogram. However, in order to do this, because it came from a table, it needs to be done as summary data. So what you need, the way you do that, you have to go back to the spreadsheet, and then it's menu, try again, make sure that I'm in the spreadsheet. Under data, one of the options is summary plot. And you can choose what you want. I want X, and I want probability. I don't want, you can either have a split page, but it would be getting pretty small. So new page, okay, and you've got your histogram. And then it's just a matter of adding the sliders. So the sliders are under Actions, Insert Slider, and you can have a slider for N and P. So that's how they were created. So because you've got the activities which you can download and use at your leisure, I thought that I'd concentrate on showing how these things were created during today's webinar. All right. So, something else that I thought I'd demonstrate, which isn't part of this activity, although I think there's probably an activity somewhere on the website that covers this. It's binomial coefficients done dynamically. So I've got a notes page, and in a notes page I can insert sliders. It's just a matter of going to menu, insert slider, and then formatting the slider. And you can also have these maths boxes. Now, a maths box enables you to also add, to do calculations, but the advantage of doing them in a maths box in the notes application over using the calculator application is that the calculation is dynamic. If you change the value of one of the variables, the calculation changes instantly. So if I just, in my maths box, if I press enter to evaluate the maths box, 4C2 has a value of 6. If I change that to an R and I do a sequence for R from 0 to 4, as I've done in the next one, then I get a list with all of the values for 4C0 through to 4C4. Now, why stick to only 4? Wouldn't it be good if I could change the value? Instead of having 4, I could have any number n, and then I could have the whole, all the binomial coefficients, or if you like, the whole row of Pascal's triangle. So I've got the same thing. I've just replaced the 4's with n's, and n is going to be controlled by this slider. So when I execute, 0C0 is 1, then the coefficients associated with n equals 1, n equals 2, and so on. And because the slider has decimal values, the answers come out decimal. If you want exact values, you can just type in exact or select exact from the menu, and you get non-decimal values. Now, the other thing you can do is, what about if instead of sticking to just one row of Pascal's triangle, why not choose a whole range of values from, say, 0C0 through to 10C10 and everything in between in Pascal's triangle? So all I'm doing is just nesting a sequence within a sequence. So now I want my n to go from 0 to n. But that's a problem because I can't use the variable n. I can't say n going to n, so I'll just give the variable a different name. I'll call it k. So I want k to go from 0 to n, which means that here I need k as well. And now I get a whole array. I'll go to the next page where I've just got, okay, I've got less there, so it's easier to see that. So I can go from 0C0 and just add more and more rows to Pascal's triangle. So I get an array, which gives me Pascal's triangle, which is rather cool. And then, of course, that's an activity that you can even do with students before VCE. on finding patterns in Pascal's triangle. So, for example, one pattern is, what if I have the sum of a row of Pascal's triangle? Well, let's have a look. So I've got the sum of these values. So starting with 0, C0, the sum of that is obviously 1. The next row, which is 1, 1, 2, 4, 8, 16, 32, and so on. And students soon see that the sum of the rows in Pascal's triangle follows 2 to the power of n, which is another rather neat thing for them to investigate. Okay, so that's binomial coefficients. In this presentation, which I'll make available to be sent to participants, I've also included some work on the inverse binomial, but it's going to take too long to do that as well. But there actually is a video in the TI Australia YouTube channel which covers exactly this material, which was recorded a couple of years ago. All right, so but for today's webinar, I'll continue by looking at the continuous distributions. So first of all, we're going to look at setting up a PDF notes page, which students can not only use for the activity, but they can also have on their calculator and use in the exam at the end of the year if they wish. And we'll also look at interactive PDF graphs and the interactive normal distribution and the rescaling of the normal distribution to the standard normal. So this is the activity which will be going up on the website in the very near future. So it's got carefully worded questions for students to follow the instructions, and there's the TI-Nspire file that they use in order to get the answers. Okay, so that's the current formula sheet, which includes the median. The reason I included that is to point out that in the revised study design, which will be implemented from next year, the median is no longer explicitly mentioned for a continuous distribution. However, examiners can still ask questions such as, find the value of n such that the probability that x is greater than m is equal to 1/2. There's no reason why they can't ask that sort of question. They just can't use the word median because it's not explicitly mentioned in the revised study design. Okay, so this is one that you could set up yourself. This is one that I've set up. I've already put in a function and the low, so which bits are above 0 or greater than 0? Well, it's between 2 and 6, so they're pretty crucial. The first thing is ask, is it a PDF? Does the probability equal 1? And in this case, it says true. So yes, it is a PDF. In fact, a couple of years ago, you might recall that there was a question on an exam, which actually, it was a PDF question, where the function wasn't quite a PDF. It was close, but not quite. So if I change that to 3, it now says false. It's no longer a PDF. All right. So that's one way of students checking that there is no input error in typing in the function. And we can see the same thing here. If that's just the graph of the PDF, and I've got the integral underneath. So that's just in a graphs application. I've entered just a normal function. Where are we? There you go. Okay, so that's just the function that I've defined as f of x. So there's nothing fancy about that. However, these lines here, they are entered as relations. So x equals a, and what I've done is I've got the x coordinates of a and b being controlled by these sliders. That way I can change the area under the curve by changing the values of a and b. All right, so the next thing is to calculate probability. So students have a template like this already set up. They can put in their values. So here, for example, 2.4, and press enter to evaluate, and this one is 4.5, and it gives you the answer, and I've stored that as a variable PR. If you want to round, this is another tip for students in the exam. Often students lose marks because they haven't rounded to the right number of significant figure, to the right number of decimal places rather. So there is the round command in Nspire. So the variable PR round to 4, except they have to be careful. I deliberately chose this value, even though Nspire returns 0.381, obviously for the exam they would have to write 0.3810. That's the only catch with doing that, with using the round command. They really still need to understand what they're doing. Okay, the mean, so the high and low is still valid. We know that, so rather than trying to integrate from negative infinity to infinity, which Nspire tends not to like, you only need to worry about integrating between 2 and 6, because that's where the function is greater than 0. So that's already in there, and we've stored that as mu. And if you want to round that, you can use the round command. The variance, do the same thing. You can have the formula already in there, so that all students need to do is press enter, edit the function, they can put in a new function, and there it is, and they can round as well, and the standard deviation being the square root. And they can have it set up for working out the inverse PDF. In other words, for example, the probability that x is less than d equals 0.5. Now that can still be asked in the revised study design, so long as they don't use the word median. So here I need to go to my, I can go to my low value, and this is 0.5, and that's my value there. So that should be the median, or the halfway mark. And students can then go to the graph and see the equivalent. They can see what the calculations they've been doing, which they can't necessarily visualize what's going on. They can now visualize what's happening. So that was that calculation that we did earlier, the probability that x was between 2.4 and 4.5. Well, they can see what's going on there. Now, how did I create that area there? That's just integral. So integral in the in the graph application, it's analyze graph and integral, and then you just choose your values. And then what I did was I linked the x coordinate of the lower value to A, which is controlled by the slider, and for the other value I did the same with B. So this one was the mean. Students have calculated the mean, and they can now see that the mean is this value here. And wouldn't it be interesting to see what happens if I change A to 2, or any number less than 2, and change that value there. Now, with the slider, as well as manipulating the slider, the other thing you can do is you can edit the value. So I'm just going to copy that value and put it into there. And we see that, in fact, in this case, the mean, the area between the mean and or less than the mean, is less than 0.5, which is not surprising because the distribution is asymmetrical, unlike the normal where we would expect the mean to be right in the middle. Okay, so likewise with the standard deviation, giving some sense to the standard deviation. So I can, what about if I copy that, Control, I've already stored, in that notes application, mu and SD are stored values. So if I paste that, it evaluates what that value is. And for this one, I just need to do the same except change it to a plus. So I've got the mean plus standard deviation. And for this particular distribution, about 65% lies within one standard deviation. I could change that to 2 standard deviations and see what happens. Make that 2. And about roughly 97% is within 2 standard deviations. Slightly different to what you would guess with the normal distribution, which is a perfectly symmetrical distribution. And there's other things as well in that activity that students are asked to explore, but they're just a couple of the sorts of things that students are asked to do. Okay, and then comparison of the mean and median. So that one is the mean. We can see if you have a look on the left-hand side, when you hover over it, it says x equals mu, and that's the median. And we can see that the mean and median are slightly different. And in fact, if we change this to 2, oops, just type in 2. And for this one, I'll choose this, the value of the median. We see that we get roughly 0.5. It's not exactly 0.5 because of rounding error, but it's pretty close. All right. So the next part of the activity is to do with the normal distribution. So it's been set up so that you can manipulate mu and sigma. The only trouble is you can't use sigma as the variable in a slider because sigma is one of the reserved variables. So I've used S instead. All right, so here I've got the mean and 1 standard deviation either side of the mean, 2 standard deviations, 3 standard deviations. And you can see the effect of changing the mean. and the effect of changing the standard deviation. And on the bottom scale, that's rescaled for the standard normal. So that's the Z scale. And what I'm hoping that students see from this is that the Z scale is a relative scale, so that it moves along so that the mean is always 0 and the standard deviation is always 1. And it doesn't matter what shape it is, the area doesn't change, as you would expect with any PDF. Now, a few other things. Now, I've entered that. That's an integral to work out the area underneath. Now, if you hover over an object and you press Tab, it will locate everything else that's nearby. So that curve is a normal PDF using X, mu, and sigma, or S in this case for the slider name. If I hit Tab again, in F1, I've entered the full equation for the normal PDF. And what students should notice is that, in fact, it's exactly the same as normal PDF. So what the normal PDF function, the inbuilt normal PDF function in Nspire does is it's just basically saving you the trouble of inputting all of that. All right. And then the activity asks students to work out various probabilities as both in both the general the general normal distribution and the standard normal. And these values here are quite handy because you can change A for different areas, and you can also change the value of mu and the standard deviation. So they can use this to work out probabilities and see what's happening visually. And of course, if you want a value that is not in the slider value, you can just edit the value that you want. So for example, in particular, if you want 2 standard deviations either side of the mean, the area under the graph is 0.954. So that's 95% between 2 standard deviations either side of the mean, and so on. Okay. The other thing that it asks students about is the transformation from the normal to the standard normal. So if we take a point, such as this point here, with coordinates P, a point P with coordinates x, y on the normal, and x dashed or z and y dashed in the standard normal, how does one transform to the other? So by looking at particular examples, I can see, for example, that when mu was equal to 8, on the z went to 0. As well as that, mu plus 1 standard deviation was 8 plus 2, which was 10, but the corresponding z value was only 1. Why? Because it was 10 minus the mean, 8, and then divided by 2. So it was a translation by 8 units, which is the value of the mean, and a dilation of a half related to, which is 1 over the standard deviation. And so it starts to make sense why the conversion is z equals x minus mu over sigma. Now, what about the translation? If you dilate parallel to the x-axis by a factor of a half, but the area has to remain as 1, then you obviously have to dilate by the reciprocal amount in the y direction. So if you halve parallel to the x-axis, you have to double parallel to the y-axis in order for the area to remain constant. And so therefore, students can see where that transformation comes from. So transformations is one of those themes that applies throughout methods. It isn't just something you do at the start of the year. Okay, so students can work through that activity, and those manipulatives are there for you to have a look at your leisure. All right, so the other thing I just want to talk about briefly is statistical inference for sample proportions. Now, there are 3 activities already on the website. As well as that, there's also a video which relates exactly to this presentation here on the TI Australia YouTube channel. So I'll just very, very quickly go through what this is about. So we're assuming, we're looking at sampling from a large population where the sample size is 20 and the true population, the true proportion, the true population proportion is 0.5. So if we take a sample, sometimes this time we got 12 successes from a sample of 20. This time we got 9 successes. That time we got 10 successes. So the number of successes will vary from sample to sample. So then it goes through and about defining the random variable p hat, which is the proportion of favourable outcomes, if you like, or the proportion of successes, and comparing the x value with the p value. It's just the same thing. One is the proportion, one is the actual count of successes. And if we collect this data, so what I've done here is in a spreadsheet, I'm collecting each of these samples. And this line here is the mean. So I start, that line there is the mean. So initially, the mean, which is this line here, so that's the mean of those 2. I've only taken 2 samples so far. So initially, it jumps around all over the place. But as the number of samples increases, we see that it converges towards 0.5, which is the true population proportion. And with this, students can reset and do it many times, and they realise that yes, if you repeat the sampling many times, then it will tend to the true population proportion. Okay, and that's just the program that I used to create it. I'm not a programmer, so it's probably pretty clumsy, but it doesn't matter, it works. And they're just some other things that students can work through in the activity. They're just exam type calculations. All right, so okay, that's just showing the same. There's some algebra to show the theory behind all that. That's all covered in the activity. And then, well, what's the effect? We've seen what's the effect of changing the number of trials? Sorry, the sample size. So that's a sample size of 10. So I'm taking 200 samples of 10. So these are all examples of how it works. And increase the sample size, and what we're hoping students see is that the spread is much less. So if you want to be more certain that your sample is going to be representative, you want a large sample size. And this is the same thing done in a histogram. And the reason that it's, I think, important to do this in a histogram at this stage is because we can see that it's actually a bit like the normal distribution. So it brings us to the approximate normality of the sampling distribution. So one way that we can see how close to normal it is, rather than just a visual inspection, one of the things you can do with Nspire is if you select normal probability plot, so that's just you can just click on the graph and you get the context menu, which is control menu. One of the options is normal probability plot. And what this shows is a line, which is what the values, where all those points should be if it was exactly normally distributed. We can see that it's not exact, but it's not bad. But interestingly, if I increase the sample size, it actually gets better. All right? It's very, very close to normality. And this is the same thing, but just done as a histogram. So we can see the effect of changing both N and changing P in this one here. So here, changing the value of P and changing the value of N. So we can see that when P is close to 0.5, it's much more symmetrical than when it's either close to 0 or close to 1. Okay, so the approximate normality works best when the true population proportion is approximately 0.5. And okay, so that just goes through the approximate normality and so on. But and the activity covers that quite thoroughly. And lastly, it's confidence intervals. So each of those values of p hat, each of those dots, is just a point estimate. And it's unlikely, it's possible but unlikely, that the point estimate is going to be exactly equal to the true population proportion. So what's better than just giving a point estimate is to give a confidence interval, an interval within which the true population proportion is likely to be found. And in political opinion polls, that's exactly what, if you read the fine detail, that's exactly what they provide. They provide a confidence interval and that's just some of the algebra, which in the activity is done thoroughly, but there's this manipulative, which shows the confidence interval and the area under the normal distribution. So if we go to 90%, so if we want 90% confidence, the study design specifically mentions the 90 and the 95%. We see that we use a Z value of 1.64, so that's where that comes from. For 95%, I know that we sometimes say to students that it's 2, but in fact, it's a Z value of 1.96 is the one that they should be using in methods. And that's okay. So this one here, where the true population proportion is 0.65, and I've created this animation where I draw one sample, and that's the confidence, that's the 90% confidence interval from here to there for that particular sample. And we can see that, yes, it crosses the green line, so it does contain the true population proportion. And I keep selecting samples. So far, they've all contained the true, until now, they'd all contain the true population proportion, but that one doesn't contain the true population proportion. Okay. And each time students do this, because it's a random number generator, they should, if it's done randomly, they'll get slightly different results. So we saw that there were, out of 50, there were about 2 that didn't contain the true population proportion. So from that, students might gain a better understanding of interpreting the meaning of a 90% confidence interval. Means that in the long run, approximately 90% of confidence intervals will contain the true population proportion, and approximately 10% will not. Therefore, the probability that a random confidence interval contains P is approximately equal to 0.9. So it does not refer to a particular calculated confidence interval. It's about the process for obtaining that. Okay, so I think I've gone over time, so I'll leave it there and just encourage you to download those activities when you receive the link. So thank you very much for attending.
Terrific. Thank you very much there, Frank. That's really, really inspirational, particularly, of course, highlighted by those visuals that you were able to manipulate because of all of those sliders that you set up. I can see that people will be looking forward to the publication of those activities. Yeah, and of course these things they're really for teaching the concepts. It's not just for working through to get a result. It's teaching the concepts, and that's where it's so very much illuminating. I quite like that norm PDF command. It took me a while to discover that. I was earlier typing in the entire formula for the normal distribution until I found that norm PDF command. Yeah. And the links between discrete, and then continuous. You had the histograms and then building up to continuous, which of course we can then use our integral calculus for finding the area under the curve. Great stuff, all nicely tied together. So attendees, this is your last opportunity now to type in any last minute questions to Frank into the chat there, direct to all panelists, or you could just direct to Frank, or you could just wish him well and thank him for what he has shared with us this evening. Reminder that we still have many more to go in our 2023's revised study design VCE series. The dates and topics are on your screen now, and the web address up in the top right there, Texas Instruments Australia. And of course, this event, along with all of the others, was recorded. You can find that for reviewing later on, either on the TI website, past webinars on demand, or on the TI Australia YouTube channel. Thank you all for attending, and once again, thank you to our expert panelists, Frank Moyer. Good evening to all.
Good evening.